What's up, everybody? Welcome back to Chapter 3, all about perturbing torques affecting the spacecraft in low Earth orbits. Okay, so last time we had looked at the magnetic perturbing torque and how to express that in the body fixed reference frame in terms of its X, Y, Z components, such that we could plug this back into Euler's equations of motion and use that, say, in a numerical simulator to propagate forward the attitude of the spacecraft or to obtain the time history of the attitude of the spacecraft. So today we're going to first dive into the second perturbation, which is in 3.2, the aerodynamic torque. Or in other words, the drag force being converted into a torque, or in other words, the interaction of the spacecraft with the Earth's atmosphere, and that is highly relevant for a low Earth orbit where the spacecraft is known to experience a lot of drag and therefore would experience a lot of aerodynamic torque. The first thing we need in order to calculate this torque created by the residual atmosphere on orbit is to have a model for the atmospheric density. Okay? Now, if you look at any aerodynamics textbooks, you'll figure out that there are a lot of atmospheric density models out there that have been derived by researchers, including one from our research lab here at Carleton. But for all practical purposes, the most common atmospheric density model is the so-called exponential density model. Which allows someone or anyone to calculate the atmospheric density denoted by rho equal to some reference density, rho naught, times the exponential, hence the name exponential density model. Exponential of what? Well, exponential of minus the current altitude of the spacecraft, and that is geodetic altitude. Remember our discussion of geodetic versus geocentric. So that one is measured perpendicular to the ground, even though the Earth is in a perfect sphere. Okay, so geodetic altitude minus some reference height, h naught, over the scale height denoted by capital H, like that. So very simplistic model, yet accurate to, I would say, 90–95% of the actual atmospheric density on orbit. So we need to know our current altitude, and that's pretty much it, because based on the range in which altitude we end up operating in, say we are in low Earth orbit, and we know that our Z is going to be comprised between, say, 200 and 250 kilometers over the time span of the spacecraft. So that would be range of Z. And the reason why we know in which range our spacecraft would typically operate is because based on that range, we need to refer to tables included in some textbooks and also reported here in table 3.1. called exponential atmospheric model, because based on the range we're going to get a different reference and density as a constant value specific to that range. This is varying, and same for the reference height or altitude, okay, which is going to be a constant for a given range of operation, and exactly the same for the scale height. Okay? So everything is constant, but this variable, which will then influence the current calculation of the atmospheric density, rho. Okay? That is the first thing we need to obtain in order to be able to calculate the aerodynamic torque applied to our spacecraft. Once we have this piece of information in our back pocket, we are ready to then look at the aerodynamic torque in specifically the body fixed reference frame. And again, the reason why we want this torque specifically in the body fixed reference frame is because we know that this torque will then be able to be plugged directly into Euler's equations of motion as we had derived it in chapter 1, which again was all in the body fixed reference frame. Okay, well, the net torque experienced by the spacecraft in the body fixed reference frame, so denoted by tau A for aerodynamic torque in the body fixed reference frame, is going to be simply the summation of all individual aerodynamic torque experienced by all panels of the spacecraft. Okay, and typically a spacecraft is of a cubic shape, more or less, and therefore will have 6 panels. If you were to have spacecraft with 20 panels, feel free to just add the individual torque components for the 20 panels, but here for demonstration purposes, I'm assuming that I am only dealing with 6 panels, okay? And the upper script K here only denotes the current panel number, okay? So that could be referred to panel K1, K2, K3, and so on for the 3 remaining panels of this cubic shaped spacecraft. All right, components, of course. So now, how can I calculate the torque experienced by one panel specifically, so that I can repeat the procedure for all 6 and then sum them all up to get the net torque? I'm going to look at the individual torque on a single panel. Is going to be calculated based on the drag force or aerodynamic force in the body fixed reference frame experienced by that given panel K. And you know that a force is actually, or a torque is a force times the lever arm. So we're going to do the same kind of principle here by multiplying this with C in the body fixed reference frame for that given panel, and skew symmetric. So this is our cross product of 2 vectors turned into component form. Hopefully by now this is kind of walking apart for you. Now this term here denotes the position of the aerodynamic center of pressure for that given panel, expressed with respect to the center of mass of the spacecraft, okay? So we have our center of mass of the entire 3D spacecraft. Then we draw a position vector that points directly at where all of the aerodynamic force in that given panel could be concentrated on a point, yet result in the same effect. And that specific point here is known as the center of pressure, in that case aerodynamic center of pressure. So that position vector for that given panel is going to be expressed in the body fixed reference frame itself. And all panels would have a specific aerodynamic center of pressure location, which all have to be measured with respect to the origin of body fixed reference frame and expressed in that particular reference frame. So this is what your CB in terms of X, Y, Z components and body fixed refers to, and you do that for each panel. And then once you have that for a given panel, you do the cross product of the aerodynamic force that is being experienced in the body fixed reference frame for that given panel. Okay, well then let's go down the rabbit hole and let's have a look at what we need here. So we're going to say where the aerodynamic force or the drag force in the body fixed reference frame for that given panel, it's just going to be obtained from the aerodynamic force or the drag force, but expressed in the ECI reference frame and turned into body fix through the attitude matrix CBI. Okay? Not too difficult. And the reason why we rather calculate the drag force in ECI is because this is simply what we know. So that would be the drag equation. Okay? So let's keep looking at the unknowns until we find that we have everything to go backwards and figure out the net torque and the body fixed reference frame applied to the spacecraft. So then I'm going to say where my drag force in ECI for a single panel is going to be one of two things. Okay? Either 0 if the panel in question is not exposed to the flow, right? So if you have the spacecraft like this, flying in that direction on orbit, obviously the top panel will not be experiencing any drag. The bottom panel will not be experiencing any drag. The back panel, same thing. Both side panels won't be seeing any drag. The only panel that will be experiencing drag is the frontal panel. Okay? Or maybe I should have drawn it the other way around. So that would look something like this. Okay? So that's your velocity vector with respect to the atmosphere. Then the only panel that would be seeing drag is this one, because that's the only panel being exposed to the flow. That's what I mean here. So only one out of the total 6 panels would have a non-zero drag. All the other ones would be 0. So for the panels, I'm going to say otherwise. If that panel in question is indeed exposed to the flow, then we're going to apply our drag equation minus 1/2 rho density, which we can obtain from the exponential model as seen previously, times drag coefficient, where for cubic kind of shape object on orbit, we're talking about CD that ranges between 2 and 2.3, typically, more or less, okay? Times the cross-sectional area of that given panel in meter square. That would be this side times this side. Obviously get area facing the flow for a full panel. Then typically we see V square for drag, but to be very accurate, we're going to talk about velocity relative to the atmosphere, because the atmosphere is spinning. So even though a spacecraft could theoretically have 0 velocity on orbit, because the atmosphere is spinning, then that would kind of create a drag, okay? So that's what this thing denotes, VR. And furthermore, because we're talking about components here, our 3x1 column matrix, and this is where our 3x1 column matrix would come from the components of this relative velocity expressed in ECI. But then, where is the V square? Where the V square is actually buried within the cos of an angle denoted by alpha for that given panel. All right. So this is slightly different than the typical drag equation you see. 1/2 rho CDA V square. But it turns out to be equivalent, okay, when in terms of components. So let's first have a look at V relative and ECI, like that. This is relative to the atmosphere, which is modeled as being stationary with the Earth. So as the Earth spins about its spin axis, North Pole, or IZ, then we pretend that the atmosphere would rotate at the same angular velocity. So for that reason, I'm going to take the components of the spacecraft velocity in ECI, like that, minus the angular rotation of the Earth about its spin axis as a scalar, cross product with the spacecraft position components in ECI. And all this means that you will have to use a two-body equation of motion to propagate the orbital states forward in time. Those are position velocity components in ECI, as seen in orbital mechanics, such that you have all you need here to calculate the relative components of the velocity with respect to the atmosphere expressed in ECI. This is simply 2 pi per day converted to radians per second. I mean, that is an approximation, of course, but that gives you a good number to begin with. Okay, so this is VRI. So we talked about all these terms inside our drag equation. The last one is cos of alpha k. Well, alpha k, or cos of that, is actually the dot product of two vectors. Okay, so if you have your spacecraft and you are calculating drag for, say, that panel here, what you need to do first is to define a vector normal to this area, okay? And that vector is going to be a unit vector normal to this panel, okay? And that one is going to be denoted by n vector for that given panel, like that. Okay, and then you have the relative velocity vector, say, coming in like that. VR vector, such that the trick is to take the dot product between those two vectors, such that you could evaluate the cos of the angle that those two vectors make, alpha. And whenever alpha gets to 90 degrees, then we consider that that given panel is not seeing the atmosphere anymore, and thereby is not experiencing any drag. But whenever this angle is between pi over 2 and 0, essentially, then we consider that this panel faces the atmosphere or faces the flow and therefore is seeing drag, such that cos of this angle for that given panel is going to be just applying the dot product in those two unit vectors, okay? So because here I have only cos in terms of the dot product, that implies that the two vectors I'm taking the dot product are going to be of magnitude 1. That's a unit vector. My n vector is unit vector, so that's fine. VR, however, is not unit vector, so I need to normalize it with its magnitude like that. Okay? So that would give me cos of the angle between those two vectors. And I can then plug this back into my drag equation. And that becomes actually my deciding criteria to see whether or not a panel is exposed to the flow or not. Okay, so instead of just looking at it from a discussion perspective, we need to turn that into equations. And that would mean that whenever cos of this particular angle is less than 0, okay, or in other words, between pi over 2 and minus pi over 2, we consider that anywhere where we have this velocity vector relative to the atmosphere, that the angle that this vector makes, always with respect to n, as long as it's not equal to pi over 2 or larger than pi over 2, then we're good, in the sense that this panel would be experiencing drag, and here we're going to say otherwise. So in MATLAB Simulink, you just do an if statement, calculate that. If this condition is satisfied, then you say drag is equal to this, otherwise it is equal to 0. Okay? And that's how you calculate this, use as a deciding factor and use within the calculation of the drag force in ECI itself. Now, dealing with vectors is not the most practical thing, so what we're going to do here is turn these vectors in terms of their components in the body fixed reference frame by writing that this n vector can be expressed in terms of x, y, z components seen with respect to the body fixed reference frame that has its origin at the center of mass of the spacecraft. So you take that vector in red and you report it along the body fixed reference frame, and you figure out its direction for its components, like that. And the dot product of two vectors turns to be components of the first one, transpose, times components of the second one, like this, over the Euclidean norm of VR components in the body fixed reference frame, like that. Okay? But because we don't have VR in the body fixed reference frame, but instead we had just calculated the relative velocity components in the ECI reference frame, it means that we're going to rewrite that expression as the normal vector in terms of its components for a given panel, transpose of that, times the attitude matrix CBI, times what we have obtained previously, which is components x, y, z of the relative velocity vector expressed in ECI. And don't forget to divide by the norm of this 3×1 matrix, like that. Okay? So, to go back, the first thing you do is simulate the orbit to get positional velocity of your spacecraft in ECI at any time. Then based on that, you calculate those three components for the relative velocity vector. And then you define all your unit normal vectors for all panels in terms of the components in the body fixed reference frame, based on the attitude matrix that you would get at the end of kinematics. If you remember the block scheme diagram I had drawn on the board a couple of lectures ago, where we had the dynamics block, calculating omega dot, integrating to get omega, feeding kinematics with omega, and then integrating the derivative of the attitude representation. Well, then you could obtain the attitude matrix, use that in that expression to get cos of this angle. Based on that, you do an if statement and you check. If the cos of the angle is less than 0, it means that the geometry between the relative velocity vector and a normal vector is more than pi over 2. Otherwise, the relative velocity vector is coming from the other side, because then the angle will be more than pi over 2. But if that's not the case, you can calculate drag for that given panel. Rho has to be calculated based on the current altitude or based on the current components of your position vector in ECI using the exponential density model. And once you have that altitude, then you have all the ingredients to figure out the density at that given altitude using the table provided in the lecture notes. Okay? CD will be given to you, but typically between 2 and 2.3 is a good first assumption. The frontal area or cross-sectional area for a given panel is solely based on the spacecraft three-dimensional dimensions. This was obtained from before, so then you have everything you need to calculate the drag force in ECI experienced by each panel, and then you turn that into the body fixed reference frame. And once you have the force due to drag in the body fixed reference frame, obtained from the attitude matrix, obviously, what you need to do is to define or ask your structural engineers what will be the position of the aerodynamic center of pressure along each panel, and then you figure out their position with respect to the origin of the body fixed reference frame, do the skew symmetric of that times the drag force in the body fixed reference frame for that given panel, and that will give you the torque and the body fixed reference frame for that single panel, and then you sum them all up, and that will give you the net torque in the body fixed reference frame caused by the interaction of the spacecraft with the atmosphere of the Earth. Okay? Now, as you go higher and higher in altitude, say you're talking about an apogee of 30,000 kilometers, don't even think about calculating drag or aerodynamic torque in that situation, because the spacecraft is so far from the Earth that there is no residual atmosphere at that point. Okay? So this aerodynamic torque in terms of perturbation only exists for low Earth orbits. Okay, so whenever the spacecraft is close-ish to the surface of the Earth. Okay, that's it for aerodynamic torque. Not that difficult. The trick was really to figure out if a given panel is experiencing drag or not, and again, this is just done by taking the dot product of the relative velocity vector and the unit normal vector for a given panel, and then you check that condition. Okay, so let's move on to then 3.3, which is about the next perturbing torque for Earth orbiting spacecraft, and that would be solar radiation pressure torque. And again, the objective would be to obtain that in the body fixed reference frame to use it in Euler's equation of motion. As the name implies, this perturbing torque is due to the interaction of the spacecraft with the sun's photon, due to the fact that the sun radiates photons in space, and those photons reaches the vicinity of the Earth and thereby reaches the spacecraft and create a force which is a non-conservative force and thereby would remove orbital energy from the spacecraft. Okay, so one of the key parameters to look at calculating solar radiation pressure in terms of torque in the body fixed reference frame is to have a way to calculate the spacecraft sun vector, and for that we're going to use a model provided by JPL, the Jet Propulsion Lab from NASA. Okay, so if you look at the geometry here, you have the Earth, you have the spacecraft orbiting quietly along its orbit around the Earth, like that. The position vector between M1, the primary attracting body, or the Earth, and the spacecraft, as you know, is your R vector. Okay? The sun is way out there. Mr. Sunshine, always happy, but still spitting photons everywhere in space, and those photons will eventually reach a spacecraft and slow the spacecraft down, or accelerate it depending on the direction with respect to the flow of the photons. Okay? The position of the sun with respect to the Earth is denoted by R, subscript S for sun, like that. Okay. So the spacecraft sun unit vector model, we're talking about the unit vector that goes from the spacecraft to the sun like that, and that one's going to be denoted by S. Okay? Where S is a unit vector. So in terms of head-to-tail summation, we can say, just by looking at this diagram, that RS is going to be the summation of R let me do the other way around. It'll be easier. I'm going to solve for S, which is going to be equal to RS minus R vector. But because this is a unit vector, it means that I need to divide this by the norm of that. Okay? And that would give you the spacecraft sun unit vector. So we can easily determine the position vector of the spacecraft along its orbit through the two-body equation of motion, and you would integrate that twice to get the position. Nice. But what about the sun's position with respect to the Earth? Because the Earth moves with respect to the sun on its orbit, right? So depending on the year, the month, the day, the hour, the minute, and the second at which we'd like to calculate that, we're going to get a different answer. Turns out there is a high fidelity model that can allow us to figure out this parameter given time at which we want it. Okay? The algorithm is provided again by NASA JPL and is provided in the lecture notes as a set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 equations filled with a bunch of intricate numbers like 0.01, 999, 46, 43, or 1.9, 14666, 471. So those are empirical numbers that were used to derive this high fidelity model that would allow us to predict this vector at any given time. So the only thing you need to feed the algorithm with is the time at which you want this vector, and you have to specify it in terms of year, month, day, hours with 2 digits, minutes, and second. I'm not going to give you the details of the algorithms and copying those big numbers that at first sight don't make any sense because that would just be a waste of your time and my time. But the algorithm, given the time, is just provided in the lecture notes. Feel free to refer to it should you need to calculate this position vector yourself. It's just a plug-and-play procedure. So given this, you do that, and then based on the result, you feed it into the next equation, and so on, such that at the end of the day, you get out of the NASA JPL algorithm for this vector, you get it in a component form, which is good news. Okay? So you get this vector expressed in the ECI reference frame, which means that based on that, you can now go back to your S vector and express it in ECI reference frame by using the vectrix notation, obviously. So you're going to need RS in ECI provided by the NASA JPL algorithm based on the time, and minus components of the position vector in ECI obtained from the numerical integration of the two-body equations of motion over the Euclidean norm of Rs in ECI components minus R in ECI in terms of components. Like that, okay? Now, skipping forward 12 equations, you can now, based on this, figure out the torque due to solar radiation pressure on the entire spacecraft. So the procedure is going to be very similar to the way we had calculated aerodynamic torque. So in other words, we're going to do the summation of all, say, 6 panels, and then go from torque to force, and force and body fix down to force in ECI, and then apply the solar radiation pressure equation in that, and then go backwards and figure out the torque onto the spacecraft, okay? So the solar radiation pressure torque, denoted by tau s, in the body fix reference frame, is just going to be equal to the summation of the torque due to solar radiation pressure in body fix experience on all, say, 6 panels, okay? Where the torque experience and body fix due to solar radiation pressure on a given panel is going to be obtained from the force due to the photons hitting the spacecraft, and force in terms of x, y, z expressed in body fix, with which we're going to take the cross product of the solar radiation center of pressure on a given panel. Remember, that is the position vector that goes from the center of mass of the spacecraft to a given panel center of pressure for solar radiation pressure, specifically, where the net force could be concentrated on a single point and still generate the same effect. So that is the location of that point, referred to as a center of pressure. And cross product in terms of vector, or skew symmetric in terms of components. That is given to you such that you need to figure out solar radiation pressure and body fix for a given panel, obviously. Okay. It's going to be obtained from the attitude matrix, CBI, from solar radiation pressure force in ECI for a given panel. So it looks a lot similar to the aerodynamic torque development we did in the last section. Okay. And this is where the solar radiation pressure force equation will be used. We're going to say that FSI in a given panel is going to be either 0 or minus P AK eta SI, and this is where this spacecraft sun unit vector expressed in ECI is very useful, okay? And you get that from the long NASA JPL algorithm provided in the lecture notes, provided the time at which you want to calculate it, times cos of the same angle, which is the angle between the unit normal vector for a given panel, but this time with the spacecraft sun vector S. And you apply this equation whenever a panel is experiencing solar radiation pressure, or in terms of equation, that will be whenever cos of this angle is larger than 0. Otherwise, you say that there is no solar radiation pressure affecting that specific panel. Okay? Now, what are these parameters? Well, P denotes the solar pressure per unit area. Okay, so this is an average value of the sun's effect on spacecraft in the vicinity of the Earth, and that value is actually equal to, or approximated to be equal to, 4.51 10 to the negative 6 Newton by meter square. A is a cross-sectional area of the panel for which you're doing the calculation. Eta is the absorption coefficient. Okay. If you talk about white aluminum panels, that value ranges between 0.2 and 0.4, but that is just for generic aluminum panel coated in black paint and white paint, but that could vary quite a bit for other type of material used to coat spacecraft panel, okay? But if nothing is provided to you, I mean, just use, say, 0.3 and keep going with the calculations. Okay? So for completeness, although I mentioned it, cos of the angle here is very similar to how we had used it for the aerodynamic torque. So I'm going to say cos of this angle for a given panel is obtained by the dot product of the unit normal vector for that given panel, okay, dot product with the sun vector. But because we don't necessarily have that available to us in terms of generic vector, we'd rather play in terms of components. That one in the body fixed reference frame is easily obtained. Dot product turns into transpose of the first one times the second one. Turns out we don't have the spacecraft sun unit vector in the body fix, but instead we have the sun spacecraft vector in ECI. And for this reason, we need to use the attitude matrix right here to turn this component's object into, or from ECI to body fix. And that will give us cos of this angle used in the actual calculation of the solar radiation pressure force in ECI, but also used as a deciding factor to determine if a panel is exposed to the sun's photons or not. All right? So that's pretty much it. This is calculated, if we summarize the algorithm, this is calculated from the NASA JPL algorithm in the lecture notes. This you know how to get. This is the attitude matrix, instantaneous attitude matrix for the spacecraft with respect to ECI. This is determined just by the shear orientation of body fixed reference frame with respect to all the panels. So that can easily be determined. That gives you this that you use inside of that. This is a constant. This is based on the spacecraft dimension. This is provided to you by the structural engineers. This is coming from the NASA JPL that was calculated, so you can get this. Turn that into forces in a body fixed reference frame using the attitude matrix, and then turn that into torque using the CB direction vector in terms of the body fixed reference frame that refers to the position of the solar radiation pressure center for a given panel, and turn that into solar radiation pressure torque in body fix, and then just sum them all up, and that will give you the net perturbing torque due to the spacecraft interaction with the sun's photon. Okay? So now that was the third perturbing torque that we can practically evaluate and use in a numerical simulator that we've studied. the last one is going to be what I think the most interesting one is the gravity gradient torque. Due to the fact that the gravitational force is actually a function of the distance between an object in space and a primary attracting body, that difference in force will create what's known as a restoring torque. And that's what we shall now have a look at in 3.4, gravity gradient torque. And surprise, surprise, we're going to seek an expression for that in the body fixed reference frame to be used with Euler's equations of motion. Okay. So to do that, well, let's first have a look at that from a conceptual point of view. Okay. So say you have the Earth down here, and you have what's referred to as a dumbbell spacecraft, which is an imaginary object on orbit that looks like that, and is modeled with 2 point masses connected by a rigid rod, M1, M1 like that, or M2, rather, M1, M2. And what's going to happen is that because M1 is closer to the ground than M2, the force being applied onto M1 due to gravity is going to be larger than this one. And as a result, we're going to get a restoring torque in this direction about the center of mass of this imaginary spacecraft. Okay? That torque will be acting on the spacecraft until the spacecraft passively aligns itself such that both masses are directly collinear with the line of action of the gravitational force. Okay? At that point, there won't be any restoring torque applied because both, say, F1 and F2 will be collinear, whereas here they weren't. Right? Because if this is the center of M1, you see that they are kind of creating an angle as well. Whereas here they go through the exact same line all the way to the center of the primary attracting body. So this torque is referred to as a restoring torque, due to the fact that gravity decreases with respect to altitude. There's a gradient of gravitational force being applied throughout sorry, a spacecraft orbiting about a primary body. Nice. Now the question is, how can we figure out this restoring torque or the gravity gradient torque in the body fixed reference frame? Okay, well, let's first consider a small element of mass within a rigid body. That's your good old blob. It refers to a rigid body on orbit. That's M1, such that this is R. Okay? And if you consider a small element of mass within this rigid body, denoted by dm, and if you refer to the position of that small element of mass with respect to the center of mass of the rigid body as rho, then we can apply our two-body equation to this and say that the gravitational force, a small gravitational force applied onto our dm, is going to be equal to r minus mu times r vector, but r of what? R of the small element of mass with respect to m1. So head to tail summation would tell you that this is simply r plus rho. Okay? over the norm of R applicable to this dm cube R plus rho cube. And because I said that that was a force and that is an acceleration, I just need to multiply this with the mass or the small element of mass. Okay? Now if you look at what we have the position vector of the spacecraft, center of mass R. And within this we have a small relative position vector of dm with respect still to the center of mass of the spacecraft. And obviously because we have this being much, much smaller than R, it means that if we were to apply a Taylor expansion to the term which lies on the denominator of that equation, it would mean that the Taylor expansion of this could be approximated simply to be 1 over R cubed minus 3 rho dot product R vector over the norm of R, or the distance between spacecraft and M1, the primary body, to the power 5. Such that this, and this is true again, the Taylor series expansion. There you go. Okay. Or alternatively, I can rewrite that as being R plus rho vector norm to the negative 3. Same thing, being approximated to be 1 over R cubed times 1 minus 3 rho dot product R over R squared, like that. Such that I can use that back into my new two-body equation applicable to a force instead of acceleration and applicable to a small element of mass instead of the spacecraft itself. So I'm going to say that dF is going to be equal to minus mu R plus rho times dm over all of this, over 1 over R cubed is 1 minus 3 rho dot product R over R squared, like that. No, sorry, that is 1 over, so I don't need to divide it by that, I just need to multiply it. Sorry about that. So let me put it first on 1 over R cubed times mu times R plus rho, like that, and then times the bracket 1 over 3 rho dot product R over R squared, all this times dm. And there was a minus, obviously, minus mu. Okay, that looks about right. Let's keep going. Such that this is a force due to gravity gradient, but that's not what I want. And not only this is a force, but a small element of force applicable to dm. So instead, what I'd rather have is a torque. And hopefully you remember that a torque is just the lever arm cross product of the force, okay? And in this situation, the torque is due to gravity gradient, denoted by tau g, like this. So we're going to take rho as our position vector between the small element of mass and the center of mass of the spacecraft, because we want that torque to be the torque about the center of mass of our spacecraft. So this distance, cross product with a force, but we need to take the integral over the entire volume to turn that into the net torque, okay? So essentially we're summing all the individual contributions from all the small dm within the rigid body. Or say that this is going to be the integral of the entire volume of rho cross product with all of this. So cross product of minus mu r plus rho vector over r cubed, and then this multiplying 1 minus 3 rho dot product r vector over r squared, boom diddy boom, and the m. Okay? So next I'm going to distribute my rho cross product term inside of that and write that tau vector due to gravity gradient is going to be equal to the integral over the entire volume of rho cross product minus mu times r plus rho over r cubed. Okay, but if I want to distribute this, I need to also distribute my dm like that, and then plus the integral of rho again, but this time cross product with this contribution here, okay? And that is going to be cross product of, and let's not forget about the 1 here, which is going to be multiplied by the hold on a second, mu. So I've got this. That's my 1. Okay, that's my 1, but then I need to do this all over again with this guy here. So that is going to be rho cross product, open the big bracket. So 3 mu times rho times r, this times r plus rho as well. So r plus rho. All this divided by this times that, which is r to the power 5. And we shall not forget about a small element of mass like that. So I just distributed my rho cross to turn this into the summation of 2 integrals. And apparently I made things worse. Okay? It was all nice and compact here. I just expanded it. Why would you want to do that? Well, you'll see why. Because now within this, we're going to have a bunch of rho cross product rho, and that gives us, if you remember chapter 1, the null vector. Furthermore, it can be shown that the integral over the volume of rho vector dm ends up to be equal to 0. Such that if we apply this and that into that big equation, you will get for tau g something which is now a lot more compact and nice. It looks something like this. We have rho cross product with r dot product of r dot product with rho times dm. Which I'm going to rewrite simply by flipping those two vectors around and bringing a negative sign in front of everything. Okay. So let's do that simple step. Tau g vector equal to minus 3 mu over r to the power 5 of the integral over the volume of not rho cross product r, but r cross product rho. And then, oh sorry, there weren't no dot product here. That was just a vector multiplying a scalar, okay? And that scalar happens to be the dot product of r with rho, like that. Okay. So that is the vectorial equation that would allow us to predict or calculate the net torque vector applied to our spacecraft about its center of mass due to the gravity gradient effect, or due to the fact that gravity decreases with altitude, and therefore across the entire rigid body of the spacecraft, we do indeed get a gradient of gravitational force, okay? But again, that's not very practical, so we rather have the component form of that equation. So for that purpose, I'm just going to look at all the vectors involved in that equation and express them in terms of their components in appropriate reference frame. In that case, we're going to select the body fixed reference frame, all vectors for obvious reasons by now. Okay. So transpose of the vector to body fixed reference frame times component of this in the body fix. Similarly, for r vector, we're going to use vectors b transpose components of r vector in body fix, and same for rho. We're going to say rho is going to be transpose of vectors b times rho in the body fixed reference frame. Inserting these back into that expression on top will give me, okay, now I'm assuming that you can easily turn this into components by writing everything with the vector c's, factoring out the vector c's, taking the dot product on both sides with the vectors b and canceling everything. But by now, it should be straightforward to do it just by that, just by looking at that. So minus 3 mu over r5 times the integral over the volume of rb cross prod or skew symmetric of rho b times rb transpose times rho b and dm. Okay, that's 3 mu r5 and over volume rb. Okay, so turns out that this result here could also be written by flipping the order of those two and taking the transpose of both, meaning that torque gravity gradient in the body fix can also be expressed in terms of 3 mu over r5 times the integral over the volume of rb skewed rho b components, and then rho b transpose and rb. Why am I allowed to do that? It's because I can say that r vector dot product with rho vector is perfectly equivalent to rho vector dot product r, and that this one here turned into components would be rb transpose rho b, which is what I had here, but this is also equivalent to this in terms of components, which would be rho b transpose times rb, and that's why I can do that. Okay? Next up, I'm gonna take this one out and this one out of the integral as well, because they won't be influencing the integral, because the integral is over the volume dm of rho, rho being the position of the dm element of mass. So the position of the center of mass of the body RB will not have any impact on the integral terms. I'm going to say minus 3 mu over the norm of the position vector to the power 5 times RB cubed, an integral of rho b times rho b transpose. I'm going to pull my dm in and then take my RB here outside of my integral. Ah, we're almost done. It's looking nicer, isn't it? Okay, now I'm going to use the identity that says that one column matrix A skew symmetric with another column matrix B is actually equal to, and skew symmetric here, equal to B times A transpose minus A transpose B, and identity 3 by 3. Well, look at what I have here. I have one column matrix 3 by 1 times a column matrix 3 by 1 transposed, which is essentially this. I'm going to solve that identity for B A transpose and say that it's just AX BX plus AT B identity 3 by 3, and use that within that expression to rewrite it as tau g body fixed reference frame minus 3 mu r5 position of the spacecraft expressed in terms of the body fix, skew symmetric of that. And then this turns into two terms. So I'm going to have two integrals. Oh boy, keep making things more complex than they were before. Where is this heading? Well, you'll see. Just have faith. So here are A and B are exactly the same thing. So the first term will replace what I have. The BA transpose is going to be A skew, B skew, or in other words, in my case, integral over the volume of rho B skewed times rho B skewed like that, times dm inside the integral and my RB outside of it. Now I had another term, so twice this, okay, essentially. So the other term will be minus 3 mu r power 5 RB skew symmetric, open the bracket, integral over the volume of, now this here, which is going to be rho B transpose, rho B, dm, this times RB multiplying the integral. Okay. Boy. Next, I'm going to play a little bit with the last term of that equation on the right-hand side. Minus 3 mu r5 RB cubed times integral rho B cross rho B cross dm times RB. And here I'm going to say minus 3 mu over R5. And then I'm going to pull this back inside the integral. So integral over the volume of RBX rho B transpose rho B. Pull this one inside the integral over again, RB, and dm. Okay. Now, if you look at this term here, transpose of a 3x1 column matrix times the column matrix itself, okay? That happened to be a scalar, which means that that scalar could be put anywhere, essentially. It doesn't need to be in the center like that. So for that reason, I'm going to just rewrite this term I have here slightly differently. And for completeness, I'm going to write the entire equation all over again. Why? Because it is so much fun. Right? Yeah? Thank you. Okay? Equal minus 3 mu R5 RB's cubed times integral over the volume rho B's cubed dm RB, and this I'm going to write as minus 3 mu over R5, and I'm going to put the RB terms next to each other and the rho B after these or before the RB, so I'm going to write this, okay, integral over the volume of rho B transpose rho B times the R terms next to each other, like that, and dm. Why did I want to do that? Well, that's because this thing here is essentially a cross product of a vector with itself in terms of vectorial operation, but written in terms of components. So this then becomes a 3x1 column matrix filled with a bunch of zeros. Isn't that a good news? Yes, because that altogether cancels this term. Yay! I made things worse to make things better in the end. All right. So the next step is simply to pull the minus sign inside here and write that this is going to be equal to 3 mu over r to the power 5 RB skewed, integral over the volume of what? Over minus, right? That minus was now pulled inside of rho B skewed, and dm. Yep. I'm going to put that in brackets times RB position components. Now, finally, we're there. Do you see the light at the end of the tunnel? I see it, because we are pretty much done with the derivation of gravity gradient torque in body fixed reference frame. Because all we have to realize here is that this thing here is actually the definition of your inertial matrix. Yes, yes. Meaning that the net torque about the center of mass of the spacecraft due to gravity gradient expressed in the body fixed reference frame is just going to be equal to 3 mu over the distance between the planet and the spacecraft itself to the power 5 times that position vector expressed in the body fixed reference frame, skew symmetric with J, the inertial matrix, times the position vector between spacecraft and the planet expressed in the body fixed reference frame. And that one is for sure the easiest perturbing torque to simulate in MATLAB Simulink, because all you need really is the inertial matrix of the spacecraft. It's a 3x3 matrix. guess what? That will be provided to you. And you need a two-body equation of motion that to be propagated forward in time to get Ri after the double integration process. Remember that from orbital mechanics. For the inertial acceleration in terms of components in ECI was obtained from the minus mu Ri components over R cube, and this was being fed back in. Now that you have this, you can turn that into position in body fix, RB, through C bi rotation matrix, or the attitude matrix, by just a simple multiplication, and then calculate the Euclidean norm of RB components to get R, and then you have everything you need to calculate the torque. Simple as that. Okay? Boy, that was fun. That was fun. But what's coming up in chapter 4 and 5 are going to be even more exciting, believe it or not. In chapter 4, we're going to look at ways that we can spin a spacecraft to passively stabilize its orientation in 3D space. And then in chapter 5, we're going to look at active control systems or feedback control systems and apply all the great theory you saw in the course feedback control systems, specifically for rigid spacecraft active control. Okay, so that concludes this chapter on perturbing torques applied to a spacecraft due to the fact that a spacecraft evolves in the natural environment, i.e. space, which itself is creating perturbing torque onto the spacecraft. We looked at the magnetic torque, we looked at the aerodynamic torque, we looked at the solar radiation pressure torque, and lastly, we looked at gravity gradient torque. We're going to see that one of them is going to be very beneficial for us, but let's save that for the next chapter. Until then, as usual, keep up the good work, and I'll see you soon. Goodbye.